So, hello everyone. If you couldn't solve yourself the last exercise in this section, the exercise number 3, then I am going to show you the main points for the solution. So we have this setup and we have to realize this. Controller sensor are 1, so it's just a simple wire, and this is the system. So I define a transfer function with these parameters. So I read from the Word document 0.5 here, 1 here, then 0.11 here, then 0.001 here. I can make it larger. Okay, and here we have a transport delay of 5 seconds. I connect these two blocks. I can excite this with a step signal. Also, then we can check the stability. So I go like this, and I check the output and the input with a scope. So I connect this, that one here, voila. I run, and what I see, this 10 seconds time is not enough. Then maybe try 100, see what happens. Again, it's still not enough. Then try 1000, what happens? Yeah, and you can see, yes, we need to sample very long time to have a response, and there is a problem that this is very slow. And to improve the properties, we can use, for instance, PID, and so forth controllers. Okay, let's start. So we will have to design a controller, a P controller. So we will have only gain with 45 degrees of phase margin, and we have to apply 20 degrees Celsius for the reference signal. I'm a little bit lazy, so I just copy paste the previous setting. Okay, then we note that the final volume will be here 20, and we will use a P controller. So here I open the loop, and I will add a term called add. You can use sum or any other blocks, it doesn't matter, plus minus. So the minus we will use for the feedback loop. And closed loop control is usually used to improve the stability and improve the parameters such as settling time, oscillations, and so forth. Okay, so we have these blocks, and here we need to add a gain. So it's a simple P controller like this. Then we look at the closed loop stability, and we see that the system became unstable in closed loop. So we had a very slow system, and now we have an unstable system, and we will use PID controller to make it stable and faster. So in order to do so, we will analyze the bode diagram. So I use the original setup just for the convenience, and here I choose this linear analysis port, open loop input. Here I choose open loop output, and I can add a bode diagram. And what is very important, as we discussed, that in the algorithm options you choose use exact delays. Apply, and I can show the plot. So as in the test, you should be able to read all the parameters. No, I am going to read only some basics. So we see that the static gain is here, and we check what is now the phase margin. So for the phase margin, we have to look for the crossover frequency. So where your magnitude graph crosses the 0 decibel. I am using the mouse, and I am more or less here at 0. I am looking, yeah. So it's quite close. You can see here the magnitude value and the frequency is 0.7 rad per sec. So I look in the phase diagram. Also here at the same frequency 0.7 rad per second. Go. It's somewhere here. If you have Windows computer, you can use also the keyboard. But anyway, we will see that the phase is here minus 377. So our phase margin is negative because it's smaller than minus 180. So this is the reason why this system in closed loop unstable. And now I want a controller which has 45 degrees of phase margin. In order to do so, I have to look at the phase where I would have 45 degrees of phase margin. So this is minus 135 here. So I am here at frequency 0.067. I look at the magnitude graph also at the same frequency. 0.06. Okay, I think it's almost there. So what I read here, it's 30.7 decibel. So if I drag this graph and move down with this 35.7 decibel, then I would have here the new crossover frequency. So this is what I am going to do. So 35.7 decibel. I change the gain. I use the formula from the class. So 10 to the power 35.7 over 20. And this would be a movement to positive direction to up, to magnify. But I have to make the signal smaller. So I go in the negative direction. For this, I use the reciproc, 1 over the same expression. Okay. Then we can check if the bode diagram changed. Either we add here new input-output ports, or I copy this gain function to the original setup. It's up to you what you prefer. I am now a little bit lazy, so I just copy this and I insert here. Okay, so we changed our body. We saw that this was the old. Then I look back and now I check what is the phase margin with this new gain. Then I look here 0.06, so here we are around 0 decibel. Then I go to the same frequency and we see indeed it should be now stable with 45 degrees of phase margin. Okay, let's test it. And what we see is the following, that the system now is stable, much faster. So remember that the settling time was something here at 1000 seconds. Now it's around 200 seconds. So I can make this scope figure a little bit better and I limit the time to 250 seconds. And the difference between this output process variable and the desired value, the reference or set point, is the error. You can use the formula from the slide or from your book to calculate it analytically, but here you can read the difference between this point and this point in steady state is the steady state error. So as you can see, it's quite large. We can also zoom in. We can use cursors. It's up to you. And what we can do with, for instance, PID controller that make it fast and accurate. In the next exercise, we can create multiple versions of this P controller with different phase margin and to compare these results. I will show only the 15 degrees and the 19 degrees phase margin case, and the 60 you can do yourself. So it's not that difficult. We have already the 45 degrees, and I am going to name this line phase margin 45. Later, I will use this signal for the oscilloscope. Okay, then we start from the original setup when we had no controller, and I go back to the bode diagram. And I do exactly the same process. I look where I would have 15 degrees phase margin. So if you forget how to calculate, it's very simple. You take your calculator. We know that the phase margin would be null at minus 180 degrees, yes? And if you want 15 degrees, then what you do is 15 minus 118,